All right, let's continue talking about conditional statements. So we talked before about conditional statements, about writing the converse, the inverse, the contrapositive, about negation of statements. Well, as it turns out, when we have definitions, we can write it as a conditional statement in the if-then form, or as its converse. And both the conditional statement and the converse are going to be true when we use definitions. And let's look at an example. We'll use the definition of perpendicular lines. If two lines intersect to form a right angle, then they are perpendicular lines. So let's write the conditional statement. If two lines intersect to form a right angle, then they are perpendicular lines. Now if we take the converse and reverse our hypothesis and conclusion, we get if two lines are perpendicular, then they intersect to form right angles. This is going to be especially helpful to us as we move along through this section. All right, so let's look at some examples, and we're going to use the diagram here to determine if they are true or they false. Angle JMF and angle FMG are supplementary. That's true because they form a linear pair. And by the definition of a linear pair, they're supplementary. Okay. Point M, this guy right here, is the midpoint of segment FH, which goes through here. And that is false because we know nothing about the length of segment FH. So we cannot conclusively say that it's the midpoint or not. So if we don't know, it's false. All right, back to angles. Angle JMF and angle HMG are vertical angles. That is true. Definition of vertical angles say, and then last one, FH right here, and JG right here are perpendicular. This is the sign for perpendicular lines. We have no idea what those angles are, so it is false. Now earlier, just a minute ago, we talked about definitions and the conditional statement and the converse being true when we use definitions. Well, what that's going to create is when we have a conditional statement and its converse, both true, we can write them as a single biconditional statement. And we had to do this because of definitions, because we know they're both true. And we're going to use the phrase if and only if. These are our magic words, and we need to have them in our biconditional statement. And how it's going to look, it's going to say P, if, and only if Q. And here we got, for the symbols, we're going to use P and then a line to Q, because since the conditional statement and the converse are both true, we can go from P to Q or from Q to P, still being true. So that's our statement. All right, so up above we used the definition of perpendicular lines. We're going to use it again. P is our two lines intersect to form a right angle. Q, they are perpendicular. So just like up above, we're going to rewrite it in the conditional statement if two lines intersect to form a right angle, then they are perpendicular lines. And the converse is going to be from Q to P, so if two lines are perpendicular, then they intersect to form a right angle. Just as we had done above. But now we're going to take those two, we're going to condense them into a biconditional statement. So we're not going to use if. So two lines intersect to form a right angle if and only if our magic phrase, which we have to have, they are perpendicular lines. So by using the if and only if, we have the conditional statement, we have the converse, we know they're both true, so we know the inverse is true, we know that the contrapositive is true, and we get to stop there. So if and only if is actually less work for us when we have definitions. So let's do some more examples. Rewrite the definition as a single biconditional statement, which means if and only if. So an angle is a right angle if and only if its measure is 90 degrees. Done. don't have to worry about the other forms. All right, let's do it again. 2 line segments have the same length if and only if they are congruent segments. Makes our life easier, so we like it. So let's look at a couple that aren't definitions. If Mary is taking theater class, then she will be in the fall play. If Mary's in the fall play, then she must be taking theater class. Here we have a conditional statement and the converse. They're both true, so let's rewrite it as a biconditional statement. So Mary is in the fall play if and only if she is taking theater class. So, okay, one more, and then we'll move on to truth tables. If you can run for president, then you are at least 35 years old. The converse is, if you are at least 35 years old, then you can run for president. Well, you can run for president if and only if you are 35 years old. Much simpler than writing a conditional statement and the converse, which is why we like it. All right. So last thing we're going to do is we're going to talk about truth tables. And when we have our conditional statements, converse, inverse, contrapositives, we know that they can either be true or false in some combination. So the truth table we're going to use because the truth value of a statement is either true or it's false. Can't be anything else. So we're going to use a truth table to show us what the possible outcomes are. So we go P to Q is only false when a true hypothesis produces a false conclusion. So if the hypothesis is true and the conclusion is false, the statement is false. Otherwise, it's a true statement, because if they're both false, then that's what we expect. If they're both true, that's what we expect. If the hypothesis is false, but the conclusion is true, well, that's possible because the hypothesis is in a very narrow band. So we could have a statement that says, if your animal's a beagle, then it's a dog. Well, your animal could be a poodle. It's still a dog, but it's not a beagle. So that's the reason for that. So we're going to start at the beginning with the conditional statements. And we have hypothesis P, conclusion Q, and we go P implies Q. So P, our possible outcomes are P is true, Q is true, P is true, Q is false, P is false, and Q is true, or they're both false. So true and true and true is going to be true. Second box, true to false. Well, true hypothesis produces a false conclusion, so then our statement's false. False to true, we get a true statement, and false to false, a true statement. Because we're only looking at the statement. We're being very narrow in what we're looking at. So the converse. And the converse, we're going to have P and Q again, but we're going to have Q to P. So we can have them be both true. We can have P true, Q false, P false, Q true, or both false. Now remember, in this instance, Q is first. So both true, the statement is true. Q false, P true, this one here is going to be just like this statement here. So that's going to be true. So false to true, it's going to be like this statement here, because remember Q is first, so it's going to be false. And then, of course, false to false is true. The inverse, we're going to do P, we're going to do Q, then we're going to do not P and not Q, and then we're going to compare not P to not Q. So we get the same initial outcomes as before. Then for not P, we're just going to take the opposite of P. So everywhere P is true, we're going to put false, and everywhere P is false, we're going to put true. Same for Q. Everywhere Q is true, we're going to put false, and everywhere it's false, we're going to put true. Then we're going to compare. We're going to compare not P to not Q. So we got false and false, which makes it true. We got false and true, which makes it true. We got true and false, which is going to make it false, and then two trues is true. And we're going to do the contrapositive, except we're going to spell it correctly. So starting the same way, we're going to do P, we're going to do Q. We're going to do not P. We're going to do not Q. But then we are going to compare it, not Q, first to not P. So we go true, true, false, false, true, false, true, false. The not P's, we're going to reverse our P's. The not Q's, we're going to reverse our Q's. And then we're going to start here. So false to false is true. True to false is false. False to true is true, and true to true is true. And then when we compare these tables, we can see that this truth table and this truth table has the same results, and this table and this table have the same results. So conditional and contrapositive let's do better than that. And converse and inverse these are our two sets of equivalent statements. And we're going to stop there. Next, we'll talk about 2.2, inductive and deductive reasoning.